me just stop talking and show you the video.
This video illustrates the definition of a radian. First, begin with a unit circle. Now, consider an arc length equivalent to 1 radius. The measure of the angle subtending an arc length of 1 radius is 1 radian.
Okay, I'll stop there for a second. So, someone just came in. Let's play it again.
Oh.
Sorry, I know, but let's do it one more time for the person who just came in. I think it's really worth watching that first part.
This video illustrates the definition of a radian. First, begin with a unit circle. Now, consider an arc length equivalent to 1 radius. The measure of the angle subtending an arc length of 1 radius is 1 radian.
Okay, that's kind of the big deal, right? This angle, which is close, and I'm sorry for those of you that someone just so Mia, I definitely encourage you to watch this video later. You know, hopefully I can. Oh, you can't see me because I didn't put myself on the screen. Sorry, 1 second. Forgetting things here. You go away for a couple days and what happens? There we go. So, sorry. The angle you're seeing on the screen, that's 1 radian because the length of the arc on the circle is 1 radius long. That's kind of the whole idea. So we are talking about angle measures in terms of how long the arc on the circle is. Because it doesn't matter how big your circle is if you're talking about lengths of arc on the circumference of it. Right? You can have a really big circle or a really small circle. But if you're talking about 1 radian, that angle is going to look the same. Let me actually draw a thing real quick here before we keep going with this. So what I mean is, if you have a small circle, it's not the best circle I've ever drawn. And there's your radius of length. I don't know, let's say that's maybe 1 inch. And here's an angle, theta. And theta is 1 radian because this arc length is also 1 inch. But it would be the same if I drew a much bigger circle. This circle, let's say that arc length is maybe 3 inches. Sorry, that radius is 3 inches. And this angle, which is literally the same angle, or as well as I can draw it, that angle is also 1 radian because this arc length is 1 radius long. Okay. Questions about that?
How do we know that's true in like what example?
So my picture's not great, but the point is that we're just talking about, so really what I'm saying here is it doesn't matter how long this actually is. If this length here, which is the radius, and this length here, if those are the same lengths, then this angle is called 1 radian because this angle is totally coming from the fact that this length here is exactly 1 radius long.
It's just an equivalency.
Exactly, yeah. Okay, so let's watch the rest of it. If I can find it again. Make it big again. Okay, we'll watch it one more time from the beginning because it's good. I like the beginning part, I'm not gonna lie.
This video illustrates the definition of a radian. First, begin with a unit circle. Now, consider an arc length equivalent to 1 radius. The measure of the angle subtending an arc length of 1 radius is 1 radian. If we double the arc length, so that now we are viewing an arc length of 2 radii, then the new angle is 2 radians. Note the connection between arc length and subtended angle. The formula for arc length.
Just want to be clear. This is a word that I never liked, subtended. Subtended angle just means if you're, and I can't point to the board so everyone can see it, but if you're talking about the blue part there or the red part, the angle there is the subtended angle of this arc length. They're just saying the angle in the circle for that arc length. It's just a fancy word that's not the best. Was there a question? Or was the question about subtended? Okay.
Length is L equal radius times angle in radians. Put another way, the angle in radians is the subtended arc length L divided by the radius. In this way, the circle need not be a unit circle. For example, if an angle subtends an arc length of 12 on a circle with radius 6, then that angle has measured 2 radians, since 12 divided by 6 is 2.
So we're going around the circle.
As this video is wrapping up, the viewer should note that a full revolution is not perfectly divided into an integer multiple of radians. The closest we can come is 6 radians. Yet this comes short of a full revolution. Perhaps it is helpful to recall that 1 revolution is equal to 2 pi radians,
Go away.
which is about 6.283 radians, slightly above the integer 6 radians.
Wasn't ready for that. Okay, so questions. We're going to talk about this, but are there questions? Let's start over here. Sorry, you'll go there first.
So is the angle like constant in whatever size circle? So 1 radian is the same in whatever size circle.
Exactly what she's saying. Yes. Danny, did you have a question?
The autoplay on YouTube. So
Oh, thanks. Good call.
Yeah.
Appreciate it. I think I just closed it. Oh, what do you mean? Because
Oh, we closed it.
yeah, I did. Thank you though. I appreciate it. Olivia.
Is there always going to be like 6 parts of it?
So he was just illustrating there that if as you keep going around the circle, each radius length gives you 1 more radian. So this angle here is 1 radian.
So if you say the radian just be if you cut it into 4.
If you cut the whole circle into 4
and then
equal
one
angles.
whole part is radian, so you have 4 radians.
No, so that's an excellent question. So the answer to that question really is that the whole circle is always the same amount of radians. So let me say a different thing. Yeah. What's the circumference of a circle? 2 pi times what? The radius. So all the way around the circle, the length is 2 pi times the radius. And so the angle all the way around the circle, although we know it's 360 degrees, we could also say it's how many radians? Well, it's a little more than 6. It's this many. Because the arc length all the way around is 2 pi radians, the angle, 2 pi radiuses, or radii is the more professional way of saying that. The angle associated with that arc length all the way around is 2 pi radians. So this angle, theta, is 2 pi radians. Or you could also use degrees. Say that angle is 360 degrees. Do you have a question? Okay.
I'm asking because when I learned the first time, the spinning circle, they said it's an equivalent.
Right, and we're going to say that, but I really want you to see where it's coming from, right? Because I'm going to tell you the way you convert from one to the other, and it's just going to be kind of a rote process that you can do easily. But I want you to know this is meaningful, right? Like we talk about a radian because it's actually a thing. It's an angle measure, and specifically, the thing I usually remember isn't that 1 radian looks like, about like that. That's about 1 radian. It's close to 60 degrees. But the more helpful piece of information is that 1 full revolution, because the circumference is 2 pi radii, the angle is 2 pi radians. And 2 pi, I know is not a lovely number. It's approximately 6.28. So 1 full revolution has an angle of 360 degrees, which is 2 pi radians. And if you wanted to, although you don't really need to, but you could say it's approximately 6.28 radians. So it takes 6 radii and a little bit more to go all the way around the circumference of the circle. Okay. Other questions? You guys have some good questions. One other thing I want to say here. I should point out, this is the reason this is kind of useful is because 360 degrees is very arbitrary, right? You could have picked, in fact, there are other measurements of angles. I think there's one where you use like 100, I forget what it's called actually. I think it's like gradients or something. But you could have picked any number, right? You could have picked 1,000 degrees in a circle and divide it into 1,000 equal subsections. 360 was useful because it's very divisible by a lot of things and it's close to the number of days in the year and lots of other reasons, but it's arbitrary. This measurement is not arbitrary. The circle always has an angle measure of 2 pi radii, regardless of how big or how small the circle is. And we didn't just pick it out of nowhere. It is what it is because it's a circle. So it's not arbitrary is kind of the point. And more importantly, it's often the language we use when we talk about angles in math. So although people will definitely expect you to go back and forth between radians and degrees, most of calculus works better in radians. And the main reason for that is degrees have a unit. That little circle thing up there, it means degrees. Radians don't have that. If someone writes an angle and they write 30 degrees, you're like, okay, it's in degrees. If they write 30 and there's no degree up there, even though if they meant to, right? If there isn't a degree symbol, the assumption is always radians. Radians are what is called a dimensionless unit. Because the way you get the radian is by dividing the arc length by the radius. So let's go back to this for just 1 second. Let's say this radius was, I'm going to make up a number that's not right. Let's say this radius was 6 feet. And the circumference was whatever 6 times 2 pi is, 12 pi. Then the angle, it's the amount of circumference. I'm sorry, that was in feet, right? Divided by the amount of radius. And of course, you get 2 pi. But look what happens to the units. They cancel out. So when you're measuring a radian, you're literally measuring or calculating the arc length divided by the radius. And the thing that people say about radians a lot, you'll hear me say this, you'll hear other people say this in the future, radians are a unit without dimension because the dimensions cancel. Feet over feet cancel out. And so you just get a number. So people write like, no, I even done it here. I didn't actually write radians because that's the way it's done. I'm going to say the angle is 2 pi. The radians is implied. Okay. So that's kind of the hard understanding part. The rest of it is the less terrible calculation part. I know calculation is not always fun, but it's not so terrible. So to go from degrees to radians, you could multiply by 2 pi over 360. We usually like to reduce that fraction and make it pi radians over 180 degrees. So half a revolution, halfway around the circle is 180 degrees, or it's half of 2 pi, which is 1 pi radians, or pi radians. You go the other direction, you go from radians to degrees, we multiply by 180 degrees over pi. I always kind of think of it like any normal unit conversion. If you're converting from one thing to the other, the thing you're converting to, you want to be on top. So for example, if I was converting from 4 feet to inches, I would multiply 4 feet by the conversion with the thing I want on top. So I want inches, so I want inches on top, and it's 12 inches per foot. The feet cancel, and you get 48 inches. Same idea here. If I want to convert from degrees to radians, I'm starting with degrees. I'm going to multiply by the conversion factor that has the thing I want on top. I want radians. I'm going to multiply this by pi over 180 degrees. The degrees cancel. I don't think you need to write, like, you don't need to draw them canceling out. We can just see that they cancel. And if we don't do any simplifying right off the bat, we get 30 pi over 180. But we should simplify that. That definitely reduces the 3 pi over 18, which is pi over 6. This is a very common angle we encounter a lot in trigonometry. You're going to want to eventually memorize the fact that 30 degrees is the same as pi over 6 radians. They come up a lot. Same idea for this one, 120 degrees. We're just going to do the same sort of thing. We're going to multiply by pi over 180 degrees. And I think it's worth simplifying sooner than later. I can see the zeros, right? The 10s are going to cancel. 120 over 180 reduces to 12 over 18 real fast. So I get 12 pi over 18. And then 12 over 18, I can reduce to 2/3, right? I can cancel a 6 from each of those and get 2 pi over 3. And I should mention, I didn't write radians. You can write radians if you want to, but it's not required. On the other hand, when you're converting to degrees or when your angle is in degrees, you do need the little degree symbol. So if I want to convert from radians to degrees, I'm going to multiply by 180 degrees over pi. And the pi's cancel, and I get 180 degrees over 10, which is 18 degrees. This one looks a little more challenging, negative 3 pi over 5. So I multiply that by 180 degrees over pi. The pi's cancel again. And now I'm going to have this negative 3 times 180 degrees over 5. And I usually try to do division before I do multiplication. Meaning, I don't want to do 3 times 180. I would rather do 180 divided by 5. Dividing by 5 isn't as terrible as it sounds. When I divide by 5, what I really do is I divide by 10 and then multiply by 2. So if I divide 180 by 10, that's 18. And then multiply it by 2, that's 36. So 180 divided by 5 is 36. That's going to be negative 3 times 36 degrees. 3 times 30 is 90. 3 times 6 is 18. 90 plus 18 is 108. I don't know why I boxed that one, not the other ones. So most radian angle measures you have typically have a pi in them. Because like 2 pi is 1 full revolution. There's usually some fraction of pi, but they don't have to, right? Like we started off like about 1 radian. I might ask something like, I want to convert, I don't know, 4 radians to degrees. How do I know it's not 4 degrees? Because there's no degree symbol. So I'm going to convert that to degrees, and it's not going to be pretty. I'm going to multiply this by 180 degrees over pi. And all I can really do is multiply the 4 by the 180. 4 times 180, let's see, that's 2 times 360, that's 720. It's a fun skateboarding game I used to play in the arcade many years ago. That'll be my answer. That's all you can do. You don't want to actually pull out a calculator and divide it and get some decimal approximation. So this is my not nice answer, 720 over pi degrees. Kind of gross. But that's what you get when your radian measure doesn't already have a pi. Questions? Converting from degrees to radians or radians to degrees is not that bad. You really have to remember to multiply by one of these two things. Moreover, you should remember that 180 degrees, half a revolution, is the same as pi radians, half a revolution.
There's a middle, right?
There's a middle, pi over 2.
No, between the so we have the radius, and then the one with square root.
We're not quite there yet. We're getting there. I think what Christian is talking about is there's a bunch of angles we're going to talk about how to evaluate the trig functions of. But we're not there. We're getting there. I think I know what you're talking about. It's on the way. The blank piece of paper. I have there for a reason, actually. So right angle triangles typically have a little square in the corner to indicate that it's a right angle. And depending on where you think about your angle being, you name the sides a certain way. So I'm going to call, let me get my good deal. Let's say this is the angle, and usually theta is kind of the go-to Greek letter for an angle name. Usually they're Greek letters though. So theta, alpha, beta, right? All the Greek letters get used, but normally theta is the first choice. Alpha, beta, gamma are kind of the next obvious ones, but you could use anything. So I'm calling both of those angles theta. I'm just going to label the sides of the triangle. So in a right triangle, the longest side is always called the hypotenuse. You can also think of it as the side that is opposite the 90-degree angle. So this side right here is the hypotenuse, or H. This side right here is the hypotenuse. Now the other two names I'm going to talk about, they're dependent on where you've labeled your angle. So for this angle here, the side opposite it is over there. So here's the opposite side. For this angle here, there's the opposite side. And then lastly, the side of the triangle that's next to the angle that isn't the hypotenuse is called the adjacent. This is the adjacent. This is the adjacent. But for example, if we had labeled this angle up here instead, then this side would be the opposite, this side would be the adjacent, and this side would still be the hypotenuse. So it all depends on which angle you're actually talking about. And then we define the trig functions in the following way. Sine of theta is defined to be a ratio. It's just the opposite side divided by the hypotenuse side. Cosine of theta is the adjacent side divided by the hypotenuse side, and tangent of theta is the opposite side divided by the adjacent side. There is a mnemonic device for this. I imagine many of you have heard it. It is called SOHCAHTOA. I really try to emphasize the ka because people say SOHCAHTOA and they're like, they think it's like COH sometimes because they're like, don't say it. So I say SOHCAHTOA to make sure everyone can hear the ah part. But it's just what we just said. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And then there are the three reciprocal trig identities. So what I encourage everyone to do is to memorize these three. You definitely should know, like you should just be down pat. Someone says, what's cosine? It's adjacent over hypotenuse. Someone asks you what tangent is, it's opposite over adjacent. And those are, and sine, opposite over hypotenuse. Those are three you should just know in your heart. The other three, I don't usually remember what side, literally, like when I think about secant, like, okay, secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. That is always the way my brain does it. I've never taken the time to actually memorize which one is which sidewise because it just, I don't have space in my brain for all that. Right? You can only memorize so many things. And this is one I haven't. So when I think about cosecant, I think about the fact that cosecant of theta is 1 over sine of theta. And the reciprocal of sine is hypotenuse over opposite. Secant of theta is 1 over cosine. The reciprocal of cosine is hypotenuse over adjacent. The reciprocal of cotangent is 1 over tangent, and that's adjacent over opposite. The way I remember which ones go together, well, obviously tangent and cotangent go together, right? They've got the same word in the name. Also, quick aside, I do encourage all of you to say the full names. Humor me, make me not sad. Don't say sin, don't say cos. Tan is not terrible, but sin and cos, like, I wouldn't say they bother me, it sounds wrong. But I really do encourage you all, say sine, say cosine, say tangent. Say cosecant, secant, cotangent. It's the correct way of saying it. But if you say the wrong thing, I mean, it's hard to say, you can't say cus. That just doesn't sound, they don't sound right. It's wrong. Anyway, that's how we define these things. So literally, this is a definition. We said these are the trig functions. There's 6 of them, and here's how they're defined. They're just ratios. It's just one side divided by another side. There's 6 possible ways you can divide any 2 sides of this triangle. And we have defined them all.
Would inverse be correct?
Not well, so I would
Or
encourage you to be careful around that word, because there are inverse trigonometric functions, and I would not call them any of these things. So an inverse function is like what we talked about a week ago. We talked about finding the inverse by switching x and y. That thing, that is not what this is for sine. We very, very strongly call these the reciprocal functions, not the inverse functions. So cosecant is the reciprocal function of sine, secant of theta is the reciprocal function of cosine of theta, and cotangent of theta is the reciprocal function of tangent of theta. And it's a good idea to get used to writing them in this specific order: sine, cosine, tangent on the left, and their reciprocals across from them. And I always remember that tangent goes with cotangent, and that each of these have one that's, it's a lengthy way of saying it, but basically each trig function and its reciprocal, one of them is a co-function and one of them is not. Sine and cosecant. Cosine and secant. Tangent and cotangent. And those cos have other meaning to them aside from just the pattern I'm pointing out here. But for now, I think that's enough as far as what they are. So you should definitely memorize these, and then also learn that cosecant is the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tangent. I really wouldn't ever encourage anyone to memorize that cosecant is hypotenuse over opposites. I can't recommend it because I can't even do it. All right, so we can use these trig definitions to then find the trig functions of angles and triangles. So here's a right triangle. It's kind of the classic right triangle that everyone thinks about. It's classically mislabeled here, not mislabeled, but certainly not labeled to scale, right? Because the side that's 3 definitely looks way longer than the side that's 4. And I actually did that on purpose because sometimes people are going to draw triangles that look nothing like what the sides are actually are. So you don't want to get fooled by thinking that what they've drawn is actually what they mean. We're going to find the third side here. We're going to use the Pythagorean theorem to do it. So the Pythagorean theorem, right? If you have a triangle, a right triangle, I should say, labeled A, B, C, we have the A squared plus B squared equals C squared. What I was thinking about for this is that the longest side, which is the hypotenuse side, always goes by itself. And the other 2 sides, the legs, if you will, go together. So for this triangle, I want to find the hypotenuse. I'm going to have 3 squared plus 4 squared equals C squared. 9 plus 16 is 25. So C is going to be exactly the square root of 25, which is 5. Not plus or minus, because we're measuring a length here. It shouldn't be negative. So C is just going to be positive 5. And now we can use that to find sine, cosine, tangent, all the trig functions of this angle here. Something worth noting. I don't know what that angle is. Right, we're not saying we know that that's like 20 degrees or 30 degrees. I know from experience it's approximately 37-ish degrees, I think. Maybe not. I could go look at the calculator and figure it out, but that's not even the point. We are not being asked what this angle is. We're being asked to find sine, cosine, tangent, etc. of this angle. There. That is, yes. So if you wanted to find the angle theta here, you could use an inverse trigonometric function to do that. But we're not going to talk about that today. But yes. So sine of theta is the opposite over the hypotenuse, which is going to be 4/5. I do recommend leaving things as fractions unless it's like you could change this to 0.8 if you really wanted to. I don't recommend it. Cosine theta is going to be 3/5. Tangent of theta, which is opposite over adjacent, is going to be 4/3. Cosecant of theta. So I don't even honestly like. I'm not looking at the triangle for these ones. I'm saying, oh, cosecant is the reciprocal of that one. It's 5/4. Secant of theta is the reciprocal of cosine theta. It's 5/3. Cotangent of theta is the reciprocal of tangent of theta. It's 3/4. That's how I'm doing that every time. We got time. Let me throw another example your way. Maybe it's always closer. Let's do another one. Let's say we were given this lovely right triangle. Okay, well, we don't need that part over there. Our angle is theta here. And we're given some side. Let's say this is 5 and this is 8. Sure. And we don't know what this side is. We want to find all 6 trig functions of this angle. But before we can do that, we have to find the length of the unknown side. And I should make it clear that this is a right triangle by drawing the little square thing there. So let's find that third side. 5 squared plus the unknown side squared equals 8 squared. And because it's always the hypotenuse side that goes by itself in this Pythagorean theorem. So let's see, I've got 25 plus question mark squared. You could use x if you don't want to use question mark, right? X might be the better choice. 64. And 64 minus 25 is going to be 39, I think. The question mark squared is 39. So the unknown side has a length of the square root of 39. And now we can go about finding sine, cosine, and tangent, and the other three. But I'm going to start with sine. I really should say sine of theta, cosine of theta, tangent of theta, because there always has to be an angle that you're taking sine or cosine or tangent of. So sine of theta, opposite over hypotenuse. The opposite of theta is the square root of 39. Hypotenuse is 8. Cosine is adjacent over hypotenuse. It's going to be the adjacent side, which is 5 over 8. And thirdly, tangent of theta is the opposite over adjacent, which is going to be the square root of 39 over 5. And then the three reciprocals. I know cosecant is the reciprocal of sine. The reciprocal of root 39 over 8 is 8 over root 39. The reciprocal of cosine is secant of theta. And that's going to be 8 over 5. The reciprocal of tangent of theta is cotangent of theta. And that's going to be 5 over the square root of 39. And I should say, it's pretty typical that we do rationalize these denominators. So when you have a square root in the denominator, it's usually pretty standard to multiply this by the square root of 39 over the square root of 39 to get 8 root 39 on top divided by just plain old 39 on the bottom. I honestly don't care that much about that, but it is something that people usually do, so I feel like I have to show you that. This one I would multiply by root 39 over root 39 as well and get 5 root 39 over 39. We only do this if there's a square root in the denominator, because we only care about rationalizing the denominator. We don't care if there's a root in the numerator. There has to be a root somewhere sometimes. All right, let's look at this third page here. This page. Oh yeah, so sometimes you might use a calculator to evaluate trig functions. Sine of 2 degrees. Use the thing I want to emphasize about about using a calculator to find sine or cosine or tangent or anything is you have to make sure you're in the right mode. And if it says sine of 2 degrees, make sure you're in degrees, plug it in, you're going to get about 0.0349. If you want to see, like if you're using your phone calculator, which I don't necessarily recommend, but sometimes that's what we do because, you know, that's what we got on my phone calculator here. I want to find sine of 2 degrees. Now I'm in radians. Now I'm in degrees. And these calculators on the phones are weird. You have to do kind of backwards or less intuitively. You have to do the 2 first and then the sine of 2. There's my 0.0349. On the other hand, if I want to do cosine of pi over 5 radians, just switch to radians. I'm going to clear it out. I'm going to do pi divided by 5. Where's my pi? There it is. Divided by 5. And then I'm going to do cosine of that. I'm going to get 0.809 approximately. Again, these are approximations. Be careful, right? Someone could ask you to find sine of 30. And you might think they mean 30 degrees. But if they didn't write 30 degrees, you have to assume it's radians. So doing that in radians, sine of 30 is terrible. It's negative 0.98. Just make sure you're in the right mode and don't use your phone calculator if you can help it, because to me at least it seems very unintuitive how to use it. Maybe if you practice with it, it's very easy, but it's not easy for me. You've got a regular TI 30 whatever, I would use that because it seems easy to use. And then we get to the part, maybe not the best part, but a part that's really important. There are some special triangles. So I think of this triangle as being half of a square. Right? There's this other half of the square over here, where the side lengths are the same, because that's how a square works, right? All the sides are the same length. I usually think of them as being a length of 1, but you could also think of them being any length. And if I want to find this third side, I'm going to use the Pythagorean theorem. So I'm going to say they're 1. I'm going to say this side is the hypotenuse. And 1 squared plus 1 squared equals the hypotenuse squared. Well, that's 2 on the left. So 2 is the hypotenuse squared, which means the hypotenuse is the square root of 2. Or if they were x long, I just scale it by x and say, or it's x times the square root of 2. So I think of this as a 1, 1, root 2 triangle, also known as a 45, 45, 90 triangle. Because we took a square and we cut it in half along the diagonal, and that 90-degree angle that would have been over here got cut in half into a 45-degree angle. In radians, 45 degrees is pi over 4 radians. You want to think about it for a second, it's an eighth of a circle. Whole circle is 2 pi radians. Half of a whole circle is pi radians. Half of that is pi over 2 radians, which is a quarter of a circle, and half of that is pi over 4 radians, which is an eighth of a circle. Or you could just do the conversion, right? You could take 45 degrees and multiply it by pi over 180. That would also work just fine. Okay, well, looking at this, we can now use this special triangle to find sine, cosine, and tangent of pi over 4 radians. So sine of 45 degrees or pi over 4 radians is the opposite over the hypotenuse, which is 1 over the square root of 2, which we typically rationalize, multiply by square root of 2 over square root of 2, and get the square root of 2 over square root of 2 times the square root of 2 is just 2. So sine of 45 degrees or sine of pi over 4 radians is square root of 2 over 2, or 1 over root 2. Either way is fine. Notice that if I use the x lengths instead, I would get x over x root 2, and the x's would cancel, and I would get 1 over root 2. So it doesn't matter how you scaled your triangle. Similar triangles have the same trig values. You can make this a 5, 5, 5 root 2 triangle with the same angles. I just took all the sides and multiplied them by 5, and you'd still get the same trig value. Because sine of 45 degrees would be 5 over 5 root 2, and the 5s would cancel, and you get 1 over root 2, which would be the same. My favorite thing about the 45-degree angle, also known as the pi over 4, I know I've got favorite things about angles, yes. My favorite thing about this angle is the sine value and the cosine value are the same. Sine of 45 degrees is 1 over root 2. Cosine of 45 degrees is 1 over root 2. Again, I would rationalize as root 2 over 2. So when I'm thinking about a 45, 45, 90 triangle, or a pi over 4, pi over 4, pi over 2 triangle, which no one ever says, but okay. I'm thinking, oh yeah, 45 degrees, pi over 4 radians, sine and cosine are the same. They have the same value. And then tangent's nice. Tangent 45 degrees is opposite over adjacent, which is 1 over 1. Just 1. These are angles that people are going to expect you know the trigonometric values of. It is a very normal expectation for you to know what sine, like in future classes, not right now, obviously I'm teaching, right? But like in the future, people will be like, sine of pi over 4, you should know that. Cosine of 30 degrees or pi over 6, you should know that. All these angles on this list right here, it's expected that you are aware of what they are and know how to find them easily. So let's look at this other one. So kind of the way I find this other triangle, back this up for a second, is I start with an equilateral triangle, which has 60-degree angles, or pi over 3 radians, and I cut it in half. So this angle up here is 30 degrees, which is pi over 6 radians. And I like to say that this side length is 2. I cut this side length in half, so it's 1. And this side length here is going to be, well, I'm going to find it. 1 squared plus x squared equals 2 squared. So x squared equals 4 minus 1. So x is the square root of 3. So in this triangle, you can see mostly all that, kind of, maybe. Let me just fold in here. When I think about this 30, 60, 90 triangle, I'm always trying to draw the smallest angle as the 30-degree angle. The medium angle is the 60-degree angle. And of course, the biggest angle is the 90-degree angle. 60 degrees is pi over 3 radians. 30 degrees is pi over 6 radians. And here's how I remember where the sides go. The biggest side always goes opposite the biggest angle. 90 degrees is the biggest angle. The biggest side is 2. The smallest side goes opposite the smallest angle. The small side is 1. The smallest angle is 30 degrees. So 30 degrees over here, there's my 1. And lastly, the medium side goes opposite the medium angle. The medium angle is definitely 60 degrees. And the medium side is the square root of 3. Square root of 3 is definitely between 1 and 2. It's about 1.7. I always do this when I draw this triangle. That's really like when I draw this 30, 60, 90 triangle to help me figure out what sine and cosine of these various angles are. I literally go through that process. I'm like, okay, biggest angle, biggest side, smallest angle, smallest side, medium angle, medium side. Opposite, right? Smallest angle, opposite small side, medium angle, opposite medium side, biggest angle, opposite biggest side. And then we can use this 30, 60, 90 triangle to evaluate sine, cosine, and tangent of these various angles. So pi over 3 is 60 degrees. So I'm looking at this angle here. Sine of pi over 3 is opposite over hypotenuse. Square root of 3 over 2. Cosine of pi over 3 is adjacent over hypotenuse, which is 1 over 2. Tangent to pi over 3 is opposite over adjacent, which is the square root of 3. I should also mention, notice that we're not writing the other 3 trig functions. Right? I'm not writing cosecant, secant, and cotangent for any of these because I'm making the assumption that we can all easily find them. Right? We can find secant, cosecant, and cosecant, secant, and cotangent by simply taking the reciprocal. So I do want to mention it's really, really straightforward to find cosecant of pi over 4. Let me ask you all though, what should I take the reciprocal of? Root 2 over 2 or 1 over root 2? Right, the reciprocal of 1 over root 2 is just root 2. If I do the reciprocal of this, it's going to be 2 over root 2, and then I have to do more work to rationalize it. So, yeah. Let's get these last 3 on here. Here's pi over 6 radians, or 30 degrees. Sine of pi over 6 is opposite over hypotenuse. Cosine of pi over 6 is adjacent over hypotenuse. And tangent of pi over 6 is opposite over adjacent, which is 1 over root 3. And we should rationalize that. We multiply it by root 3 over root 3. We get root 3 over 3. So when I think about these three important angles, pi over 4 radians or 45 degrees, pi over 3 radians or 60 degrees, and pi over 6 radians or 30 degrees, there's a couple things I think about for sine and cosine. For 45 degrees or pi over 4 radians, sine and cosine have the same value. They're both root 2 over 2. For pi over 3 radians and pi over 6 radians, sine and cosine have the same interchange values, meaning one of them is always root 3 over 2 and one of them is always 1/2. So if I'm doing something with pi over 6 and pi over 3 and sine or cosine, I'm like, okay, I know one of them is root 3 over 2 and one of them is 1/2. I just have to figure out which one it is. But yeah, you will. And so something I should point out, and this is no, actually, I shouldn't. That's more complicated than we get. I guess I've said enough. So we'll definitely talk. We'll continue talking about trig functions and how we evaluate them on class on Wednesday. But this is kind of the beginning of it, right? So we definitely want to think about what the definitions of the trig functions are, right? Memorizing what sine, cosine, and tangent are, and definitely you also want to think about these important triangles because they are going to come up a lot. We're definitely going to be finding sine, cosine, and tangent of angles like these a lot. All right, that's all I got.